Hey, okay, so we're gonna go through some troubleshooting on the RainBird LXD 2-wire controllers. We're out at a job site and the system has not been reliable and not everything has worked. So what we want to do initially is analyze and get as much information as we can. A lot of times this can be done with as-built drawings that are provided by the owner. However, in this situation, and I think in most, we don't have that luxury. So we have to try to create these things with just what we know and what we have on job site. So what we're going to do initially is take a look at the controller itself and review the controller and gather as much information from the controller as we can and document it so that we can start creating and building a database, a list, paperwork that does provide us this information. So here is the controller itself. And the way that we can first do this, one of the ways I like to go through is test all stations and check systems. We'll go to 2-wire diagnostics, click next. We can go down to ping decoders and click next. Station decoders. We'll push and hold yes. This will allow us and take us to a screen that I enjoy because it gives us all the information in one spot. So I kind of clicked to a technical diagnostics screen initially, but I did this for a couple of reasons. It allows us to scroll through every station. Station number 1 has a decoder address, and that's what's currently programmed into this controller. So we'll want to document this, and then we can also ping this decoder to determine if the decoder is connected or not connected and what the results are. And so we've done this, and those results have been, I've documented those results here on my paper and created those results. And all of these results will give you and show you different things. So these are all the numbers that come down, and you can see some of these numbers differ and vary. What constitutes a good reading? What constitutes a not good reading? And what do they mean? This is the challenging part, and this is where the technician part or the doctor part kind of comes into play. So when we get an address and we ping it, and it has a prior and an inrush and a holding, this is measuring our electricity and what the electricity is doing at the time of initiation. So this prior is the quantity of electricity that the controller is consuming prior to initiating this decoder address. Upon the inrush, the controller measures the quantity of electricity that it consumes as it is trying to initiate and start this decoder and this zone valve. And then the holding current is after the valve is on. How much electricity does the controller consume as it's activating that decoder or that solenoid? When they are all three the same, that means there was never a change in the electrical consumption, which could mean several different things. Number 1, the decoder itself is not connected. Potential issue number 2, there might be an address that is incorrect. Maybe the 7 and the 3 are transposed and it should be 23337. That could be an issue. The third thing is that there could be a wire path issue in the field that's not allowing the decoder to be connected. So several different things could arise and could be the potential problem when we get a result like this. If we go to station number 2 and we look at that, we have its decoder address, we have a prior of 184, we have an inrush of 612 and a holding of 203. Now this delta, or the difference between prior and inrush, this additional 400, 500 milliamps of inrush current on this zone means that it actually responded, that decoder responded, and there was a electrical load on the other end of that decoder. So there was electricity that was consumed. That's what we would expect, is to see a large number there. And then the holding current should always be more than the prior, but should be back down much less than the inrush. So we have a prior of 184, we have an inrush of 612, and we have a holding of 203. Station number 2 is probably working effectively and just fine. This would be a good reading, meaning that good being quantified by station number 2 came on and probably is shutting off. Station number 3, as you can see, again, 214, 218, 218. This is going to be a similar result to station number 1, and there's a challenge or an issue there. Station number 4. Station number 4 comes up. We have a prior of 216. We have an inrush of 630, and the holding maintains very high at 630, which means that quantity of electricity, or that work that's having to get done, consumes a lot of electricity. And then when it goes to holding, it continues to consume a lot of electricity, which means there's a short circuit on the downstream side of the decoder. The decoder is responding, decoder address is correct, wire paths are good, and it's communicating fine to the decoder. The decoder is responding and doing its job. However, after the decoder, between the decoder and the solenoid, that's where we see a representation of this issue. There could be basically two things that we would want to evaluate in this particular situation. One, are the wire connections sealed tight and good, or are they exposed, and is there a short between the wire connections of the solenoid wires? That is a potential. The second, and probably the most common cause of this situation, is in fact the solenoid is actually shorted out. And so in this situation, station number 4, we would want to identify station number 4, inspect visually the wire connections, remove the wire connections, and then test ohms resistance, test the solenoid itself to determine if the solenoid is shorted or not. You can continue down with all of these addresses in the list of the ping results that were given on the controller. This is going to give you all of the addresses that are in the controller, which are important for us to understand. And it gives us all of them, and we find out when the last one was. So now that we have created our list and gone down our list of addresses, the next thing that we want to do is to go ahead and now start walking around the field. And we want to experience and try to understand what's in the field, what we have in the field, what valves are close, and where they are. So as we start to walk around, and I'll turn the camera around and kind of show you the field and just kind of let you in on the mindset of what we had. So we started walking around, and we were seeing this area from where the controller is. Looking around, we were able to identify a valve box over here as being the valve box that is closest to what we had. So from here, the next closest valve box is going to be over there, and then they continue on around the site this way. This being the closest one, we came to this valve, uncovered it, and we were able to see the decoders that were in this valve box. Now, one of the decoders was here. One of the decoders was not connected. So the one decoder that was connected, we were able to get it working, was fine. The second one was not connected at all. We took that decoder that was not connected, we connected it back at the controller, and just tested it directly at the controller. As soon as we connected the decoder at the controller, it did short the controller out, which basically allowed us to understand, hey, the assumption is that that decoder is bad and not working, which is why it was disconnected. So we then found another decoder that was working, and we have placed both of the good decoders in this valve box, which we will connect to these valves once we continue addressing and working on the rest of the wire path. We simply just connected the two wire paths together temporarily so that we can follow this wire path and troubleshoot the wire path more, as there's more and additional problems down the road. So we've been able to identify and discover both of these addresses. We match these addresses back to the sheet that we wrote on, and now we know that this zone is station number 1 and 6. And I will show you the map. Walk back over here to where our paper is. And behind our list here, I created a sketch. And this is the sketch of where the controller is. We have identified the backflow device, which is our water source. And then we've identified this valve box is the closest one. And this is station 1 and 6. That's station 4 over there. And as we walked around the site, we started to create and build this sketch drawing. And so we were able to identify visually in the field stations 1 and 6, stations 4. We were able to identify that this is station 2, station 7, 3. There was a ball valve over here, stations 8, 9, and 10. We were able to identify station 12, a 3-way splice, and we were able to identify 3 valves, 1 decoder, decoder 14. Now this left us with a little bit of a quandary because we were unable to identify stations 5 and station 11. And so since we couldn't identify those stations, we didn't quite know what was going on. So what we began to do at this point is disconnect the wire path from our first closest valve box. When we analyzed stations 1 and 6 and got those disconnected from the controller, we then went back to the controller and we ping tested all of the stations in the controller. Now at this point, doing this, the idea is that if we have disconnected the first valve box from everything else in the field, the 2-wire path goes from the controller to that first valve box we've identified. And then if everything else continued on, it would prove that when we ping tested everything, nothing would come back because nothing is connected. So when we did those results to prove our theory that the wire path goes from the controller to valve boxes 1 and 6, this would create the fact and prove our theory correct that the wire path goes directly there and there's nothing in between. When we did this, we discovered that station number 5 gave us a good ping test and a good ping result. And yet nothing else was coming up. So everything was disconnected except station number 5. Well, station number 5 was a zone that we couldn't find to begin with. So this was kind of a good thing. So it allowed us to know for a fact that somewhere between the controller and what we thought was our first valve box, actually station number 5, the one that we didn't know where it was somewhere in between. So as we started to then look at this, this is station number 1 and 6. Over there is where the controller is. So then we had to assume, wait a minute, somewhere in this area is station number 5. So as we started poking around a little bit more, and we discovered that the mainline water is here, likely comes this way and goes this way, we started poking around. Sure enough, underneath the mulch and everything else, we were able to locate zone number 5. Interestingly enough, in this valve box was in fact a valve that was wired to a decoder, the decoder was wired to a solenoid, but the valve was literally laying in the valve box covered in dirt. It was not connected to the pipe, so we have no idea what's going on here other than this was zone 5. So we just eliminated this, created a wire splice, knowing this is likely going to be a plumbing issue later. But right now we're just going to bypass this. So this is where zone number 5 was. We did locate it. It is now a wire splice box. And now we are able to go from, so now we have proven that the wire path goes from the controller to this location and then over to that location there. This again helps us start to build the as-built drawing and helps us build factual information that allows us and the client to have factual data to help troubleshoot things later. And this is the actual valve. There was a solenoid and a decoder connect this. This was the actual valve that was laying in that valve box, not connected to anything. All right, so that was step 1. Step 2 is to repeat this process each time we go to the next valve box. And by doing these couple of testing measures of disconnecting the wires and disconnecting the next valve box, and then ping testing the zones, we begin to start to build our understanding of valves and wire paths and what's connected to wire paths and what's not connected. This is a zone valve here, and sure enough, what we were able to determine is that the wire path does come in here and out, and the wire path from here does go right over there to that valve box. So when we connected those wires together, came over here and connected this, but then disconnected everything else, when we did ping test, we were actually able to ping and go from controller, this pinged, this valve pinged, and then nothing else pinged. So we know that the wire path goes from here to there. Now there are some other methodologies to use. The Armada or the TDR device also allows you to help understand where wire paths go. And so those are great devices. However, I wanted to go through this methodology with you guys and with the team here as we continue to learn, just using basic methods that I think all irrigators have. This really comes down to a logic and thought process, analytical process of how do we troubleshoot something using scientific methodology to ask questions, create theories, ask questions, and then perform tests that prove an outcome. And that's kind of what we did with the controller, the first couple of stations here, and we're just repeating that process through the site. What we were able to learn as we continued on this process was that the wire path goes from this valve box here. We initially thought it went underneath here and went over to those valve boxes. However, what we determined was that apparently it goes from here actually over to a valve box in this flower bed over here, comes to here, and then from here it actually goes on over to this valve box. Now this valve box is important for us in the troubleshooting and understanding of the wire path, and the reason it's important is because there are actually 3 wires that are in here. There's one cable, a second cable, and a third cable. And if you'll look at this, it's interesting because there's a smaller gauge 2-wire path, smaller gauge, but then this one gets to be larger. It's the 14 gauge, and this I believe is 16 gauge 2-wire path. So now this gets us to where we've got different wire paths. Maybe this will help us understand some things moving forward. So we were able to then take it to the next level, but from here it tees off. Now we were able to determine part of the system goes potentially one way, part wire path goes another, and we're being fed from the wire path over here, and then the wire path goes out this direction, this direction. So now we're able to start analyzing things in that way. And at this point, what we want to do is take and just energize one leg and disconnect the other leg for now. And we're just going to keep working this down one leg of this wire tree, if you will, one leg of this wire path until we get that one leg completely solved. Once we get this leg completely solved, then what we'll do is come back up the tree to this area and then continue on working the wire path strategy to the next one. So this wire path seemingly comes down to here, to this valve box here, which is a ball valve and a wire splice, but we do have, again, three, 1, 2, 3 cables. And so what we've determined is this cable here is actually the cable that goes back up to that valve box. So this cable assumingly goes this direction. This cable likely goes this way, feeding those other valve boxes over there. So again, here we've now split. We had one tree there, we chose a direction, and we're coming down here. We'll do the same thing here. We're going to split this tree, and now we're just going to work this direction until we get this completely solved, linked up to here and then there. Then we will change and revert and come to here. We will continue to work this wire path this way to get it solved. Once we solve this problem and all the issues there, then we will go back to the initial T intersection that we saw on the wire path and start to go down that direction and see where we go from there. One bite at a time, one segment at a time, slowly, methodically, verifying and testing each and every area and understanding where the problems are. Not guessing at anything, but testing and proving failure and success at each area. This is scientific methodologies that we all need to make sure that we're doing. So this is very typical as to what we were seeing when it comes to the wire connections and the craftsmanship of the work on this site. Unfortunately, we have many wire connections that were not even in gel casing and caps. We had some that were in gel cases, but the wire nuts were never fully inserted all the way down. And by not doing that, the gel doesn't completely seal the connection, which means they've made a valid attempt to create a good connection, but because it was not fully inserted, this might as well have been that, because it wasn't sealed. The moisture still got in, the moisture is still done. What's happening is that there's just not enough wire. They're not giving themselves enough material, enough conductor to work with. And so we are having to add more wire and or strip more wire back, get more wire into the valve box in order to try to make these things, these connections, cleaner and easier to get to. With more cable available to them, not being close to the jacket, but more cable available to them, you can see that they were able to fully insert this wire nut. That connection likely is going to be better than all the rest of them. What we located and what we saw here were two smaller rectangular valve boxes that did not give us enough room to work on these valves. So we also decided there were a couple of other valve boxes where there were two valves that was just valves, not filters or everything else. So we're actually going to relocate larger valve boxes on here to give us more room and space. The small boxes that were here are going to get transferred over to another location to where it's going to be easier and better to work on those. So we're going to be redoing the wire connections and stuff here, working on our wire paths there, slowly getting rid of the issues and the challenges that we saw. Now, the initial readings that I showed earlier on this were 185, 195 milliamps. what should those milliamp readings be? Well, the RainBird says that these milliamp readings for the controller itself, the controller measures somewhere between 15 to 18 milliamps with just the base module and no cables, no wires attached. Each field decoder, an FD101, will consume approximately a half of a milliamp. So if we have a system that has 14 decoders, such as our list here, we should assume the controller is going to pull 15 to 18. A field decoder is going to pull about half a milliamp. If we had a sensor decoder, it would pull about 8 to 12. So we have the controller at 15. We have 14 FD101s at about 1 or a half, which would mean this would be 15 plus somewhere between 7 and 14. We should have somewhere around actually 20 to 25 or 30 milliamps is what our reading should be. So when we do a line survey or a reading on our controller, our prior should actually be 30. Then it should jump up to 400 or 500. Then it should have a holding current of about 15 milliamps plus the original 30, which would put it at about 45. So that's what we're looking for, and that's what we're striving for, and we'll try to see if we can get there as we continue to do these repairs.